Welcome everyone to the last talk. Glad you could be here, and this is the last one, so it's pretty exciting. Today I want to present to you HyperNet, a software platform for the Internet of Battlefield Things. So the Army practically invented digital computing. Started with the ENIAC, through the EDVAC to the ORDVAC, and all the way to these exascale initiatives today. They also made great contributions to the network infrastructure with the network ping utility, as well as software platforms built on top of this infrastructure like 3D CAD modeling. The Army continues to lead the way in battlefield devices as we move into the present and into the future. As the Army creates more lethality in land, sea, and air, we have a copious amount of connected devices out in the field. Now, according to one of the Dr. Namburu from the Chief Computational Sciences Division at ARL, the Army needs to become Facebook in reverse, exploiting data for the user. Continuous innovations in scalable algorithms and software are going to play a role in overcoming distributed processing shortcomings that surface in military scenarios. Now, it's critical that the Army focus a lot of their time in these distributed processing environments because in order to maintain their edge and their leadership in the computing world, these things need to be overcome. And so what do I mean by that? Today, in a typical battlefield scenario, we have devices deployed in the field. They're generating a lot of data. They're processing a lot of data. And each one of these devices has network connections, computational power, as well as sensors to generate this data. Now, all of this data generation is great, and there's many things we can do with that, but if we do not have the processing capability, we cannot extract intelligence. So today, we need to send that data through a tiny pipeline back to our centralized cloud infrastructure to be able to process that data and get actionable intelligence back to the field. Of course, when you look at this, a massive amount of data is generated, but the thing they're computing on, this executable, is small. But we're passing a large amount of data through this pipeline to a small bit of code to actually process it. But all the data is generated on the left side. All the actionable intelligence is needed on the left side. And so what happens if you do not have access to that uplink? What if it takes too long to send your data back to the computing infrastructure? Or there may be applications where you don't even need that at all. This is where HyperNet comes in. We've turned the paradigm on its head. Instead of sending data to the code, we send the code directly to the data. With our decentralized software platform, we're able to send a small executable into the network of machines and do all the processing in network to extract real-time intelligence and situational awareness. Now, to bring AI to the battlefield requires two main steps. Step one, you must be able to deploy code to any machine.
So we're going to quickly show you what that might look like. Can we get the other screen pulled up? So this is an application that we're working on currently for the civilian market, although we think it would be interesting to work on this also in cooperation with the Army. It's an application that we refer to as Galileo. If you're into the data science realm, the name is a pun on the popular Jupyter notebooks that people use for doing data science. Anyway, the idea is that we leverage modern containerization technology to be able to deploy code projects from any machine to any machine. So for instance, I could have a bunch of different algorithms on my machine written in any particular language, and I can literally drag and drop and deploy to a particular machine. So this is what envision in your head a code or a code to data type platform might look like is Galileo.
So when we look at being able to send code to devices out in the field, the devices might be laptops, they might be vehicles, they might be a server rack, they might be embedded devices. And so one of the main hallmarks of what we just showed you is the ability to agnostically send code to any device regardless of operating system or chip architecture, and that uses containerization technology. But step two, great, I can deploy code to a machine, But now I want to be able to deploy that code to many machines, tens, hundreds, thousands, 100,000, a million. And I need each machine to cooperate with each other to actually do the processing in the network. And this is the hard part. This is what we have focused a lot of our time and our IP on, is how do you actually coordinate compute across many machines. And you may ask yourself, why has this never been done before? When you're trying to communicate across a battlefield or some internet-connected devices, the bandwidth is low. You don't have InfiniBand connections between each processor. You're doing it over whatever network fabric is available to you, but that network fabric is also faulty. Packets will be lost, communication between devices may go down, it may re-anneal, and you need to be able to handle that. Also, this device dropout and insertion. I might have a device that'll die. It's cooperating on a device, but on a computation, but the battery dies on the device. Maybe the device is destroyed. Maybe it goes offline and comes back online later on. How do you handle device dropout and reinsertion? And these three things are the hallmark of using computing assets in a deployed environment. The programming model. These three things are difficult, but if you don't have an appropriate programming model to be able to handle these faults, you will not be able to compute in an internet-connected setting. So we've spent a lot of our time generating the programming model that lets you leverage connected devices out in the field, out everywhere. And so I'm going to pass it to my co-founder, Todd, who's going to tell you more. But we've created a demo for you guys today. We'll be doing it live, up to 1,000 machines spread across the globe. And we're going to show how we can do real-time data science in an incredibly faulty network.
Thanks, Ivan. So, yeah, we just touched on this concept of a programming model, and this is actually another one of the areas that the Army has traditionally innovated in. Specifically in the context of the message passing interface. At Aberdeen Proving Grounds, we have the Excalibur supercomputer, and when you run large-scale algorithms on a supercomputer, your application is typically written with the MPI library. But the thing was, my background, PhD student in aerospace engineering, finite element analysis, started getting interested in distributed robotics. I realized that the MPI paradigm is not appropriate for an Internet of Things type of a scenario. So what we work on and what we're developing is, I would consider a fundamental technology. It's at the basic research level. We've been developing a consensus-driven programming model that would take the place of something like MPI in an Internet of Battlefield Things type context. So consensus-driven. Specifically, our programming model that we're developing is based on a mathematical principle called distributed average consensus, which comes from the distributed robotics community. And it has lots of nice properties that one would like to leverage in order to deploy cooperative algorithms into a dynamic networks. So I got some math here on the left-hand side of the screen to try and explain what this distributed average consensus principle is. The top line is the mathematical statement of distributed average consensus. It's what's called the local form, and what this describes is how a single processor in a processor swarm should update its numerical state with regards to the information that it is receiving from its neighbor processors in the processor swarm. Now, what's important to recognize from the local form is that you're summing information over your neighbor processors. And what's important here is that mathematical theorems and proofs that show that I can select my neighbors in a stochastic fashion, and I will still reach my ultimate equilibrium state, which I'm going to get to here in a second. The way to prove that is that, okay, well, I start with my local form. I can rewrite this in what's called the global form as a system of ordinary differential equations. And if you go back and look at your textbooks from undergraduate mathematics, this has a very simple solution. It's a linear ordinary differential equation, which has the following equilibrium state that has a very important form. The equilibrium state of this ODE is essentially the average of the initial condition of all of your processors. Additionally, because this system is linear, when I implement all of this stuff in code and provide it to somebody that develops algorithms in the form of an object-oriented API, you know, think I can write things in Python now and not have to worry about writing stuff at the system level, making socket calls. I'm just going to provide somebody a one-line call that they can make in Python. The equilibrium state plus the linearity of the system means that I get asynchronicity. So I now have an appropriate programming model for distributed, highly dynamic, networked environments that gives me a mechanism to perform inner products. Now, once I can perform an inner product, I can do many important things. I can do streaming matrix factorizations, which is a very important thing to be able to do in data science in general. I can do gradient descent, which is, you know, equally fundamental for the areas of optimization. You know, think training neural networks as gradient descent, particle swarm optimization, basically AI and ML more generally, because now I have a mechanism to easily perform and robustly perform inner products in a dynamic network. So, the live demo today, you know, they always say never do live software demos, but we're going to give it a shot today. The live demo is meant to demonstrate the following. We are going to solve basically a fundamental problem in data science, the classical logistics regression. We're going to be performing a logistics regression to train a binary classifier on a typical image data set. Just so you know, we're using the MNIST, the classical MNIST data set, handwritten integers, just to prove the concept here. And for those of you who are not aware of what a binary classifier is, it's just something it's a classifier that I can run on an image, and it tells me whether something is or is not in that image. Now, the way we're actually going to perform the logistics regression is through a matrix factorization approach, specifically a truncated singular value decomposition, through a novel algorithm that we developed around our consensus programming model to perform a fully asynchronous distributed singular value decomposition. So that's what we're going to hopefully show you here in a second. So let's see if we can get this thing to start up. Here's our map over here. This is where our demo is going to be happening. Each one of these dots on the screen represents a data center where we have reserved some instances for today's demo, trying to come up with the most realistic scenario that we could for today for a live demo purpose. So in each one of these data centers, I have many instances reserved here. When I start this thing, what's going to be shown is the dots are going to start talking to each other. Okay, they're going to start performing the consensus-based algorithm that we've implemented for today. Now, we hope to have 1,000 machines for today's demo, but that's the nature of the cloud. We reserve these things months in advance, and then the day of, they don't always have the resources for you, even though you reserved it. So we only have 968 for today. So I hope you forgive us for the missing 32 processes. So let's give this a shot. This machine is not on the internet. Bear with me a second. This is the live demo.
While Todd gets that together, just to point out again and reiterate that each one of these dots is a physical data center, and this is where they're geolocated. So you're going to see this consensus happening across the entire globe on the internet backbone that we have today.
Cross your fingers. There we go. Let me refresh this.
There we go.
Okay. So what you're seeing is the randomized communication protocol that is buried within our library that we've developed. So you have a fairly complex-looking communication pattern happening. Here's another view of it where you can just view individual processors happening. So each one of these is lighting up, meaning that each one of these lines between dots is an inter-process communication. So obviously this is all happening asynchronously, and then running on each one of these dots is our asynchronous logistics regression algorithm performing the singular value decomposition, which I'm going to talk about how that is actually implemented. But you can see they're all starting to have the same color, which means they've come to agreement very quickly on what the classifier is. So if we go back here to our map, we can see our quantity of interest is basically already converged. Our quantity of interest being the generalization error. This is the error on whether or not they're predicting on the test set, whether or not something is or is not in an image, which is about 6%. They're getting a 6% error rate, which is pretty classic for the MNIST data set. But anyway, here we go. Totally decentralized logistics regression via singular value decomposition on machines spread all over the world. Now, I'm going to explain to you now what's actually happening over here. So the logistics regression, you can go home and tell your friends you learned all of data science today, because all of data science can more or less be boiled down to AX equals B, where you're trying to solve for X. Now, in this context, we're going to focus on the data structure A. A is our matrix of images. X is our binary classifier that we're solving for over here in this live demo. And B is our labels for the images. So let's focus on A. A is what's called horizontally partitioned. What that means is that different sections of A are mapped to different processors. So think of A1, A2, all the way through A968 for today. Each one of those lives on a different processor on our map. Now, our innovation here was that we leveraged the theory of random sampling and the Johnson-Lindenstrauss theorem to do the following. Each processor independently generates a Gaussian random ensemble in their local memory. They're going to multiply that by their local image data set, and that's going to give them a what's called a fast local subspace estimate that, to a high probability, satisfies this inequality, which says, basically in plain English, what that inequality is saying is that Y is basically as good of an estimate of the subspace spanned by the columns of A that I can possibly get, which is a pretty amazing thing to be able to say, because I can do this essentially for free, and there's well-known theories behind why this is actually the case. Now, next step. Each processor has done this totally independently. This is where we make our one-line call to our consensus-based programming model. The processors are going to reach consensus on the average of their estimate Y for the global data set. So Y now encapsulates the dominant left singular subspace information of the entire data set, and each processor has asynchronous access to this data structure. Every time I'm making a call to one of these things, I have an asynchronous access to a new estimate of this data structure Y, which is going to be highly ill-conditioned. It's not going to be something that I want to use directly, but that's okay, because I can apply the standard QR decomposition, and now Q is a very good estimate of my truncated left singular subspace. And without going through the rest of our algorithm that we've developed specifically for the logistics regression and least squares, this is part of our IP we're developing for some civilian applications. There's two more clever applications of our consensus-based framework to basically get for free the singular values and the right singular vectors. And from there, my binary classifier comes essentially for free. Now, last week leading up to this, using our prize money we got from the last round, we were able to forward up to this 1,000 devices. We ran out of money, okay? Hopefully we would like to work with the Army to take this experimental graph to 10,000 or 100,000 to show the extreme scalability of this algorithm that we're working on. But this graph is meant to highlight something very important about our parallel programming model. Recall that I said that it is based on the mathematical principle of distributed average consensus. It has a very important mathematical property, and that is the property of scale invariance. This is going to be highly important if you want to develop algorithms for large-scale IoT-type environments. What does scale invariance mean in our context? It means that as I add nodes to my algorithm, my swarm of processors that are cooperating together to perform an algorithm, there is no additional communication overhead that is given to a particular node in that network. So, for the logistics regression example, to reach 12 significant figures of precision, each processor has to make basically 120 communications to get 12 significant figures of precision. If I wanted less precision, let's say I could do fine with 4 significant figures of precision, well, it's linear in the number of digits of precision, so I would have gotten away with something like 28 communications to reach that kind of a tolerance. But what this means is that for any algorithm that has a polynomial time implementation, there exists a breakover point where it requires less bandwidth to just do the communication in the network than if I backhauled all of the data to a centralized location and did the algorithm there. That's pretty remarkable. And if I have a very large data set and I have a processor that is sucking in lots and lots of data, it means that I can construct an algorithmic solution that says, I'm going to transmit less data by doing the algorithm cooperatively in the network than I would if I backhauled the data to a centralized location, which is pretty remarkable. Now, that breakover point is going to be different depending on which algorithm that you use, but it exists. And lastly, one thing that's pretty fascinating is that it's amenable to distributed stopping criteria, which means that if I go back to my grid view over here, you can see all of the processors are green, which means they've pretty much finished their calculation. There's no new information being injected into the system, so they've all more or less agreed. This is amenable to a stopping criteria that will allow the processors to independently detect whether or not there's any new information to glean from the network, and they can stop the communication themselves and then conserve bandwidth in your network without a human having to take that action themselves. So that's another important thing for IoT-type environments where you want to run cooperative algorithms. And so that pretty well covers the technical section. Again, I'll reiterate that what we were working on is a very fundamental technology. It exists pretty low down in the technology stack. It's a basic research question, but it has many potential capability payoffs. Okay, it could really pay off in a lot of different realms, and I'm going to let Ivan take over that section.
Great, thank you, Todd. So on that graph here, each one of these little dots, they're representing processors in our processor swarm. But really to bring this home to things we might care about in the field, I can touch on a few of these and we can have an open discussion as well in where we see these capabilities lying, because this is a foundational technology that will enable in-network processing. So one of the applications we cooked up was vehicle maintenance and repair prediction, where instead of each of these dots being a machine around the world, they are actually the embedded computer in your vehicle. And as vehicles need to be maintained, and the vehicle can start to learn locally when it needs to be maintained, it can start to share that information using HyperNet across all the vehicles, so all the vehicles will learn the global state of when they need to be predicted to be maintained or repaired. Another potential example is acoustic triangulation, where instead of each one of these dots, again, being a computer across the world, they are smart microphones with embedded processing. The processing doesn't need to be crazy. You have an acoustic event, the acoustic radiation hits the microphone, and then using HyperNet, they can triangulate around themselves using like a least squares regression to where that event occurred in space. And one of the ones that's also close to our hearts is this idea of privacy-preserving analysis of medical data. You have data that cannot be moved for privacy reasons. We can have silos of health data that have co-located computing. You send your algorithm to each one of these data silos, and they're able to learn the global state of that data that you're trying to process on top of without needing to actually move the data.
Right, and by leveraging the properties that I mentioned earlier, i.e. the linearity of our consensus mechanism and the asynchronicity of it, many times, depending on the algorithm that you're trying to deploy, you can guarantee that no information is leaked by running the I'm not leaking data from one processor to the other processor about the information that resides on my machine. So that's a pretty interesting field of research and potential application that we would also be interested in exploring.
Could you address a little bit what the minimum computing power would be needed? You said, not crazy, but, give us an idea of the amount of computing that would be needed at each of these nodes, and if in this HyperNet, when they're being utilized in this fashion, is that going to bog down their capability to do their normal function and prevent them from perhaps, doing other things?
Yeah. So one thing I'll say is that even cheap modern laptops, a Raspberry Pi, typically has enough processing power to do a significant amount of work. It's really amazing what commodity devices are able to do today. The piece we're kind of addressing here is the data locality piece. Data locality is really important for your algorithm. If the data doesn't exist where my algorithm exists, I can't learn anything from it. So from our perspective, most machines have enough power to do interesting stuff. Now, addressing your question about, well, fine, I'm going to be running something, least squares, back propagation, whatever, to train some classifier on my local data set. Is it going to bog down the machine to the point that I can't do anything else on it? That problem has essentially been addressed by containerization technology. If you're familiar with the technology is basically eating the world now, Docker containers. These things allow you to say, well, this process, easily say, somebody who's not a sophisticated cyber user, look, I don't want HyperNet to use more than 20% of my CPU time, 20% of my memory budget. I can set these things in my containerized environment. It totally encapsulates the process and keeps it isolated from everything else that I'm going to be doing on my machine. So one of the enabling pieces here isn't just the programming model that we've been developing, but it's the fact that in the last really 3-4 years, containerization has become a commodity technology. I'll give you the clicker.
Yeah, thank you. So in closing, and then we can open it to more questions, we demonstrated launching a compute job on a remote machine with our civilian application that is in beta right now that uses that containerization technology so it can run anywhere. And then once we had sent that to the machines, almost 1,000, we were able to actually do a coordinated compute job across the network. And Todd showed that this was incredibly scalable due to the mathematical equations that govern our programming model. So it's scale invariant to where each communication that needs to happen on each node is constant, no matter how big the network has become. And we would very much like to continue furthering these capabilities with the Army as we build up this foundational technology and the applications that lie on top of it. Thank you.
Hope you enjoyed our live software demo. I'm going to go ahead and turn it off because they're charging us by the hour and by the gigabyte that we're using. So unless anybody wants to take any pictures of our nice flashy lights, I'm going to terminate this process.
So could you highlight what problem you're actually trying to solve at that point?
Right. So So again, to reiterate, the particular problem these processors were cooperating on was performing a logistics regression on an image data set. The image data set that we were using was the classic MNIST image data set. So what that is, it's 60,000 images that are 28 by 28 pixels, which means that I have a feature space of dimension 28 times 28, which is 700 and, there you go. So it's a fairly large feature space, and we were fitting a binary classifier, which is a classifier of size 28 times 28 to that image data set. But the way that we were solving, the kind of the innovation here was that the way we were solving for that classifier was through an asynchronous truncated singular value decomposition that naturally leverages our consensus-based programming model and is also amenable to streaming data. So if the data set had been updated over time, this data could naturally be pushed into the network without having to stop the calculation, synchronize all the processors, and start from scratch. So that was kind of the innovation here, is that we realized there's this connection here between this consensus-based framework, which allows you to choose neighbors stochastically, and this field, relatively new field of random sampling. We combine these two fields to get these really powerful algorithms for doing matrix factorizations, which allows you to do many important data science problems in an IoT type setting. Now, we focused on matrix factorization today. You can use almost these same techniques for doing asynchronous gradient descent for optimization. Where do you want to do asynchronous gradient descent optimization? If you're trying to train neural networks for inference that are living on many different processors, you're going to be doing gradient descent. So it gives you a powerful mechanism by which you can perform gradient descent without moving the data between the processors, because that can be very expensive. Recall the breakover point that I brought up. It's a very flexible paradigm in which to develop algorithms from, and it's a one-line call for the programmer, this person that wants to develop the algorithms. It's a one-line call in Python, which is the important thing. I don't have to think about how I do all of this communication logic. That's abstracted away because that's built off of the ordinary differential equations that I discussed. Yeah. Yes, sir.
So I'm trying to understand if so take the singular value decomposition, or no, let's take the other one. Let's take the gradient optimization. Let's say
Sure.
I have an array of computing devices.
Yep.
And I want to train a neural network.
Sure.
Off some data that those devices kind of in the field have accumulated. Yep. So you send the program on how to train a neural net to those devices, right?
Right. So code to data, right?
So you've sent the program to the devices. Now, gradient descent or singular value decomposition, it's going to get to a stage where it might have to invert a matrix, per se.
Right.
Right?
Yes.
So it splits off, say I have 8 devices, it carves off chunks of that, say it's a matrix inversion step, to all of the 8 devices, or do all of the 8 devices do the same thing and they keep doing it over and over until they match?
The matrix inversion step, depending on what the application and what is the structure of the matrix inversion that you're doing, the matrix inversion happens via our, where's our clicker? The way you do the matrix inversion, right, through this paradigm, so recall, through the consensus mechanism, we extract the subspace information, and this thing is available fully asynchronously. It allows me to estimate the dominant subspace of my data set. The way we would perform the matrix inversion is that you project the data set onto that low-dimensional subspace, perform a Gramian product so that I get a small, dense, coupled system that everybody, through the consensus mechanism, that's another application, you would apply the consensus operator to that thing again, so that everybody comes to consensus on the dense Gramian of my system, and I invert in the reduced coordinates and then re-expand into my subspace Q that is the span of Y. So that's how you would perform a decentralized matrix inversion on a distributed data set, is by leveraging dimensionality reduction and the consensus operator to perform the dimensionality reduction. It's one of the, dimensionality reduction is becoming one of the foundational principles on which people develop new AI techniques. Philosophically, you want to get into why that is. Low dimensionality is basically the data science equivalent of smoothness. If you want to talk about polynomials for finite element analysis and simulation scientists and simulation science, there everybody cares about smoothness. Data science people care about low dimensionality.
Yeah, it's very interesting. I mean, finding a low order subspace, I'm trying to grasp the part of it. If I'm finding a low order subspace on just a regular computer, I can run the algorithm, DMD, POD, singular value decompositions, whatever. I'm trying to figure out how, how does processor 8, how is it coming to consensus, say, with what processor 2 is coming up with on the parts of the algorithm that have been farmed out? That's what I'm trying to.
Well, okay, don't think about it in this context as farming out, like I'm the control and I'm farming out jobs. In this sense, the problem is naturally partitioned. In our opinion, if you're talking about an IoT application and I'm deploying an algorithm into an IoT type setting, then the problem is naturally partitioned. The data is already naturally inherent in the network, and I'm sending the algorithm to that data.
So the algorithm doesn't necessarily put together your first matrix A. The matrix A has been...
The matrix A existed in the network.
Okay, and then it's...
And now it's like, well, okay, I don't want to have a bunch of complicated overlay network logic that no data scientist is ever going to sit down and figure out because that's not what they're paid to do. They want a one-line call that allows them to do an inner product in that network.
Thank you.
Thank you. So actually, we did pretty good on time, actually.
Did you pick the data centers based on cost, or
That was all we could get. We got everyone that we could. It took us a month and a half to reserve all of those, back and forth on email with people all over the world to get those data centers. We would like to we would like to find a partner that would allow us to test this not in data centers, but give us real IoT devices that we can deploy to and see how this is going to work in real physical things that are out walking around with people. But this is the best that we could do. We wanted to make sure that it was going to work today, so we used these data centers and provisioned our VMs all over the world.
Instead of accessing everybody's cell phone in Alabama.
Right.
Okay.
And getting it implemented into an iOS app, is actually kind of a lot of work, we found out, because we were thought, oh, we'll make an iOS app. People will be able to download it and do it in our demo. And we went down that route for a couple days. We quickly gave up on that. We realized we didn't have enough time to do that for demo day. Yes, ma'am.
So what would be your next step?
Well, we would like to, if the Army is interested in this, I think we would want to cooperate with the Army to figure out what the next step for us is. I would say that this is not a production grade software implementation yet, so there's still a lot of work to get into a really robust state. There's some refactoring that needs to be done as well. So next step is robustifying the code base. And then I think importantly is finding some concrete pain points, I think, with the Army that they would like to do in an IoT setting and developing the algorithms based on this programming model for those settings. I think we'd be very interested in doing that.
I had a question.
Yes.
So in one of your charts, I try to pay attention.
I hope it
did
wasn't
pay
too boring.
attention, But yeah, it just brought me back a long time ago. On every soldier a sensor, so what is your thoughts for something like that?
Right. You know, I mean, I'll give you an anecdote. My uncle is Army Rangers, and he would tell me about all the crap they'd make them wear, right? And he said, the last thing I want is more stuff to carry around. Well, they've already got all this stuff on them. It has many sensing modalities. So you have this mobile living, sensor system. Many people wearing sensors, they have networking capabilities because they have radios. So in terms of enhancing situational awareness, there's all types of interesting things you could do with deploying algorithms to run on the embedded devices, running on the things that they wear on their bodies. You could potentially get into some pretty interesting situational awareness capabilities around this idea of every soldier a sensor. Thank you.